Hello and welcome to a new video for Pre-Algebra Math UC. We're on lesson 30, which is the last lesson of the book. So that's exciting. Yeah, we've made it through the whole thing. That's pretty great. This lesson is about irrational numbers. Before we talk about what irrational numbers are though, we need to make sure we understand what rational numbers are, because basically numbers are divided into rational and irrational numbers, sort of, actually. I guess real numbers are divided up into rational and irrational numbers. And that's a whole other conversation, right? Because if we can call numbers real numbers, then that implies that there's not real numbers. And that's true. There are things that are considered not real numbers. It's kind of a weird naming system, but we're kind of stuck with it at this point, I guess. So a rational number is a number that can be written as a fraction. It's a pretty easy definition in some ways, but there's a lot to that. Another way to say the same exact phrase is that it can be written as a ratio of whole numbers, which is essentially a fancy way of saying that you can write it as a fraction, because ratio and fraction mean the same thing. And before I forget to say this lesson just basically has a lot of vocabulary. There's not actually really any problems to do. So just vocabulary and some true and false. And I guess there's some number line stuff. So anyway, so what does it mean that we can write something as a fraction? Well, we've got some obvious choices, which would be things like 1/3 or 3/4, right? Both of those numbers are fractions, so they are rational numbers. They are a ratio, meaning a fraction, of two whole numbers, 1 and 3, or 3 and 4. There's also numbers that can be written as a fraction that might surprise you. Numbers like the number 6 is a rational number because you can always put 6 or any number over 1 and turn it into a fraction. Any whole number you can put over 1 and turn it into a fraction. All right, so that's another example of a rational number. Now, what about decimals, right? Because maybe you're trying to think through and say, well, okay, these are rational numbers. What's an irrational number? Maybe decimals came to mind. So here's the deal. Decimals, a lot of them actually can be written as fractions. So even if I write down 0.25, that's a decimal, but you know what 0.25 is equal to? It's equal to the fraction 1/4. So if we have a decimal that we can rewrite as a fraction, then that means that decimal is also a rational number. There's actually a really easy way to tell, relatively easy way to tell if a decimal is something you can write as a fraction. You can tell that a decimal is able to be written as a fraction if one of two things is happening. First, if it ends, so the fact that it's 0.25 and then it stops, we'd be able to change this to a fraction. Because worst case scenario, we'd put however many decimals we have, we'd put over like 1,000 or 1,000,000, depending on how long it is. We could put it over some power of 10 and figure out what the fraction was. But that only works if the decimal ends. So the first way is if the decimal ends, that means it can be written as a fraction. The second way is if the decimal ends up repeating. So think about 1/3, for instance. 1/3, you may or may not know, as a decimal is 0.3333333333333333333 forever and ever and ever. Also known as 0.3 repeating. And we put a line over the 3 to signify that, hey, this just keeps going on forever. Well, if we notice, hey, 0.3 repeats, then that's our clue that, hey, this could be a fraction, which means it's a rational number. Now, we could end up with some decimals that are kind of weird because of, like, dividing by 7 is what comes to mind for me here. So, like, I don't know if 1 divided by 7 will do it. Yeah, so look at this really terrible looking decimal. But we've got 1,4,2,8,5,7, and then it repeats. 1,4,2,8,5,7. So it takes 6 digits before it repeats, 1 over 7 is a fraction, which means it's a rational number. But even looking at it as a decimal, if we were willing to go through the effort to write out enough decimal places, we would say, oh, this repeats, so this has to be a rational number because it has to be able to be written as a fraction. So that's kind of how rational numbers work. So then it feels like we've eliminated all the numbers, maybe, because what's left for there to be for irrational numbers? Well, one really good example of an irrational number is pi. Pi is a number that goes on forever, and as far as we know, as far as we figured it out, does not repeat. So pi is irrational. You cannot write it as a fraction. We can approximate it as fractions. 22 over 7, for instance, approximates pi to 3 places. I think 3.14 or whatever. 22 divided by 7 is 3.14. So that's a way to approximate it, but pi isn't equal to that because 22 over 7 would repeat because it's a rational number, and pi doesn't repeat. And this kind of ends up being something that I think is really cool. That like if it's something that can be written as a fraction, it has to either stop or repeat. And that otherwise, and it kind of makes you maybe think about why these are called irrational numbers, because it doesn't really make sense that we should be able to have a number that just goes on forever and never repeats. That doesn't seem very rational to me. But pi is not our only irrational number. The other irrational numbers we come into contact with are square roots that are not perfect squares. So square root of 2 would give us a decimal. It gives us something like 1.42, and then I press the square root button. 1.414213. Nowhere along the way here does it repeat in this as far as these decimals go. And someone I'm sure has looked at square roots like square root of 2 for much, much farther to confirm that they really don't end. They just keep going forever without repeating. So any square root that's not a perfect square of a perfect square will end up being irrational. So that means that we can add something else to rational numbers. Square root of 25 is rational because that's really just 5. Also, something to add to rational is we can have negative numbers that are rational, either negative whole numbers or negative fractions. Negatives are fine. The only time that we don't include negative numbers are whole numbers. We typically just are looking at positive numbers for whole numbers as a group. So pi, square root of 2, and things like that are basically our irrational numbers. So together, the rational and irrational numbers end up making up the set of real numbers. And kind of a basic definition of real numbers is that real numbers are numbers that can be represented on a number line. And so, as unpleasant as it may end up being, all of these things that I've written down up here, we could put on a number line. And it may be that we have to approximate, because we don't know exactly where it would be whenever we're talking about decimals or square roots or things like that. We might need to use a calculator to get the decimal of something, like the square root of 2. I mean, I guess I could know what numbers it's between by just thinking about, well, it's got to be between square root of 1 and square root of 4, so it's got to be between 1 and 2. But I would say, get out a calculator for any square roots they give you, so that you can see where they are. And so the opposite of a real number is called an imaginary number. And you'll learn about those maybe a little bit in Algebra 1, but definitely more so in Algebra 2. And they have interesting, what do I want to call it? They have actually really interesting applications. And this is another, I think irrational, I don't actually know for sure that this is why they're named irrational and rational, but there was a point in time in history where the idea that something like square root of 2 existed probably seemed very irrational. And in fact, Pythagoras of the Pythagorean theorem One of the things he's known for is the fact that he didn't think that irrational numbers existed, that square root of 2 wasn't something that was actually a number. So it probably as the naming convention came along, that's my guess, is that it's like, okay, it's not, these numbers are a bit irrational compared to all these really, really awesome rational numbers we have. So in a similar kind of way, we have real numbers and imaginary numbers. And at first, whenever imaginary numbers were first being talked about, probably the focus of them was that the way we graphed things at the time, there was no way to put imaginary numbers on the same graph as a real number. And so it's a name that makes sense, but now that we know more about imaginary numbers, it's not necessarily as helpful as it once was, because it kind of makes it feel like we're talking about like fake numbers or numbers that aren't real, like in a way that's not what we mean. Imaginary numbers are actual numbers that have purpose and do something. It's just that we don't encounter them in the same way that we encounter real numbers. So all that to say that real numbers we can put on a number line. So here I've got a number line, and I've got some numbers to graph. So I started off easy with just 5. Well, we'd put a dot at 5 and maybe label it just so that our teacher knows that we actually were trying to label it. Pi is approximately 3.14. So even though this is irrational, we can put it, kind of close to 3, closer to 3 than to 4, and say, okay, that's about where pi is. Negative 1.5, again, we're approximating, but we can be kind of accurate, as in, like, this should be halfway in between negative 1 and negative 2. So it's a little bit easier to be like, okay, I feel pretty confident that that's in a good spot. As opposed to graphing 1/3, which is where I have to try to imagine dividing this up into, like, thirds, right? And so this looks about like where 1/3 is. And then square root of 2, we would have to either think about other square roots that we do know, square root of 1 and square root of 4, which are 1 and 2. So it has to be between 1 and 2. Or we could put it into our calculator like I did earlier and get the decimal. So this is 1.4 and a bunch of other stuff. But 1.4 is enough for us to be like, okay, so it's somewhere between 1 and 2, close to halfway. So there, that's square root of 2. And it even says on the instructions in the workbook, the graph will be an estimation of the numbers given. We're not saying that we can graph by hand, at least, exactly where these irrational or even fraction numbers are. We're just saying that, hey, we can approximate it, and this is pretty close to where it's at. And more importantly, we do know that it shows up somewhere on the number line, even if we weren't as accurate as we maybe could have been with where we placed it. So that is lesson 30. So there's some like fill in the blank vocabulary questions, I think. No, sorry. Thinking of the wrong lesson. There's a bunch that it just asks you whether the numbers are rational or irrational. So using kind of this guide hopefully will help you with that anything that is written as a decimal that stops or a decimal that repeats would actually be rational. For it to be irrational, it has to go on forever and not repeat. So things like pi and square roots of numbers that are not perfect squares. And then it has some true false. And so hopefully we've talked enough about the vocabulary to help you get what most of those are. And then there is a number line like this. And then the last problem says optional, and the instructor book talks quite a bit about how to find square roots by hand, which is not something I can remember ever doing in my life. And I looked at it and I was like, wow, this seems complicated. And the fact that I, as someone who arguably likes math, is like, this seems complicated, that should probably tell you something. So I may do that in a separate video for funsies, but I told my students not to worry about doing it because it just seemed a bit much. And it said optional, so by all means. So that's it. That's lesson 30. This is the whole Math UC Pre-Algebra book. I think I actually skipped a couple lessons that I'll probably try to go back to. so that in the future people can see actually all the lessons all the way through. But I hope that you enjoyed this video and this series, and I enjoyed it. And I hope that you'll think about watching my Algebra 1 videos after this, maybe after a summer of rest, or maybe you just pick it up right away. But I'll put a link in the description that will take you to my Algebra 1 playlist. And it's not using Math UC, it's actually using curriculum that I created myself. And I'm pretty excited about that I'm about to actually wrap up my first year of using my own curriculum. So I hope you'll check that out. Like I said, leave me a like if you like me, or if you like math, or if you like the video, or if you like summer. If you like any of those things, like the video. And I don't know if I'll see you guys again, because, well, I don't actually ever see you, but it feels like summer because this is the last lesson. All right, bye.